Okay, in this chapter we're going to look at what are called projection matrices and also derive partitioned inverse formula. Okay, this is all within the OLS framework that was introduced previously in chapter 3. We're going to do a couple different things. First, I'll show you a method how you can derive out the individual regression coefficients. So for example, if you have two coefficients, beta 1, beta 2, remember before we could just get like beta hat equals x prime x inverse x prime y, and we got all the betas together. Now I'll show you a different method where you actually get the separate betas using separate equations. Okay, and then second, we will kind of apply some of the techniques that we use here to show that the estimator for sigma squared that we looked at previously is unbiased. Okay, so first, what do I mean by projection matrix? Well, projection, sometimes a regression is called a projection. And this is actually because you can get like a graphical interpretation of a regression. I mean, of course, if the x is high dimensional, then you kind of lose the graphic interpretation. But if there were only two x's, you can plot it in 3D space. So like if you look up, say on Wikipedia, you can see plots of, projections, like why a regression is called a projection, because you're projecting it onto the space spanned by the x's, basically. So that's where this word projection is sometimes used synonymously with the word regression. Okay, so we define this matrix, mx, which is the identity matrix minus x, x prime x inverse, x prime y. Or sorry, x prime x inverse, x prime. See, it like rattles off my tongue. So it's I minus x, x prime x inverse, x prime. Okay, so now if you pre-multiply y by mx, you see you get basically y minus, and then you've got this x, x prime x inverse, x prime y. So that's beta hat. So mxy gives you y minus x beta hat. So that basically gives you the residuals. So if you pre-multiply, any vector by mx, you get the residuals from regressing that vector on x. Basically, so this is a way of getting the residuals. mxy gives you the residuals from a regression of y on x. And that's called the projection matrix, mx. Okay, so also you can substitute in here for y. So we'll plug in the true model for y. Sorry, that's my dog. We'll plug in the true model for y, x beta plus epsilon. And you see this is x beta, and then here we have x, x prime x inverse, x prime x beta. So these things cancel. So this x beta cancels out, and you're left with mx epsilon. Okay, so you hit mxy equals mx epsilon. Okay, and remember mxy equals epsilon hat. So from this we can deduce that mx epsilon, where this is the true residuals, equals the fitted residuals. Okay, so the fitted residuals would be the true residuals after regressing on x. So all these things are equal, mxy, mx epsilon, and epsilon hat. Those are all equal. Okay, now another thing to observe is suppose we regress x on x. That would be mxx. Well, what do you get? Well, those are the residuals from regressing x on x. Right. So this residuals, I minus x, x prime x inverse, x prime x, that's just x minus x, which equals 0. Okay, so it makes sense if I regress x on x, x explains x perfectly, so there wouldn't be any residuals. The residuals are 0. All right, now deriving the partial regression coefficients. Remember, I promised you I'd give you equations for beta 1 hat and beta 2 hat separately. Okay, so define mx1 and mx2. So these are two separate projection matrices. So mx1 is I minus x1, x prime, x1 prime, x1 inverse, x1 prime. Okay, what's the dimensionality? Well, you know, let's say they're just two variables, so this is just going to be one by one, because this would be like, let's see, if it's two variables, it's like k is equal to 1. So this would be, let's see, n by k. This is k by k, so 2 by 2, and this is k by n. And this is n by n. Yeah, so this is actually n by n. Yeah, that's right. And so then, so this is, you can figure out the sizes. It's kind of important to try and keep track of what the sizes are. So this x1 is n by k, where k is 1 if it's just one variable. This is k by k, and this is k by n. Okay, so the I here is n by n. So the trick here to figuring out what this beta 1 hat and beta 2 hat are is you pre-multiply. So if I want to get beta 1 hat, I pre-multiply this whole equation, the regression equation, by x1 prime mx2 y, or just this, x1 prime mx2. I pre-multiply, okay? Now I use the fact that mx2, x2 is equal to 0, because this is the residuals from regressing x2 on x2. So that's 0. Okay, so this term is actually going to drop out. Now, what about this term? So, let's see, I think I put it in the next slide. So we're going to use, this is also equal to 0. So the reason is mx2 epsilon hat equals epsilon hat. Okay, this is, because if I regress epsilon hat on x2, x2 is not going to explain anything related to epsilon hat. And then the OLS first order condition sets the fitted residuals orthogonal to the regressor. So remember, we had a condition like this when we solved the OLS problem. So therefore, this term is also equal to 0. Okay, so I basically am left with this term and this term. So I can isolate beta 1 by pre-multiplying by the inverse of this matrix. Okay, so that's what we're going to do, pre-multiply by the inverse of this matrix. And so then you get this beta 1 hat. And now I can do the exact same operations. So this would be good to do as an exercise. So where I would pre-multiply everything by x2 prime mx1. Right, here we did it x1 prime mx2, but if I do it x2 prime mx1 and do the same reasoning, I'll come out with an expression for beta 2 hat. All right, and so these formula, I mean, it might seem more complicated. It is more complicated, clearly, than just directly solving for all the betas at once. But, you know, actually just deriving these formulas can be helpful later for when we do instrumental variables estimators. So that's partly why I'm doing this. You know, because we're going to use it later. But these formulas are called partial regression coefficient formulas. I mean, you can also, you can do regressions this way. So the interpretation is, like, suppose that I was limited and I only had a technology that allowed me to do univariate regression. So I'm not able to do regressions with two variables. Well, I could still do this regression because first I would take x2, regress it on x1, you know, so that's the mx2, x1. Let's see, this part here. This x1 prime mx2, this is the residuals from regressing x1 and x2. Okay. And these mx2, they're actually idempotent matrices. You know, so you can put in an extra mx2 here everywhere, and you can see that then this is the residuals from mx2. You know, if I have an extra mx2, so the way I could do a regression is I first take the x1, regress it on x2, take the residuals, and then I run a regression of y on those residuals. Okay, that procedure is called double residual regression. So that's basically how we can interpret this. And when we do two-stage least squares, you know, this is kind of a similar type of procedure. Okay, so now the last part of this chapter is I show that the estimator that we used, remember this 1 over n minus k, that this is an unbiased estimator, okay? And the thing that's a little mysterious about this estimator is, why do we divide by n minus k? Like, why isn't it just n, okay? So let's look, like now we're actually going to use some of these properties that we just derived earlier. So epsilon hat prime epsilon hat. So remember, epsilon hat is equal to mx epsilon, where these are the true epsilons. And we can write this epsilon prime mx epsilon, and mx is idempotent, so that equals epsilon prime mx epsilon, because mx equals mx, right? It's idempotent and symmetric, actually, the matrix. Okay, and I like this proof because it uses some really interesting properties of the trace operator. So first, let me describe what is the trace operator. So in linear algebra, the trace of a matrix is the sum of the diagonal elements, okay? So these are the properties that we're going to use. So mx is idempotent. Then we're going to use the definition of the trace. There's also a result that the trace of ABCD equals the trace of BCDA. So you can do any cyclical perturbation. And a cyclical perturbation was like I put the first element last. You know, that's like cycling through. Okay, then we're going to use the trace of alpha x equals alpha trace of x, where alpha is a number. The trace of a minus b is equal to trace of a minus trace of b. The expectation of the trace of x is equal to the trace of the expectation of x. Okay? Then the trace of an idempotent matrix is the rank of the matrix. I think we don't actually have to use use 7, but this is also, it's just something that's true, but I think the proof will not use that. Okay. Well, let me hold off. We'll see if it uses that, but I think you can do it without that one. All right, so let's look at E of epsilon prime mx epsilon, because that's the numerator of that estimator for sigma hat squared. So what's the size of this? Well, this is n by n. So epsilon prime is 1 by n. So this whole thing is 1 by 1, because we have a 1 by n by n, n by 1. Okay, and so it's just one number. And the trace of one number is that number. Okay, so this is kind of the clever part of the proof. You can stick in the trace operator. Okay, and now we can use all these trace operations. Okay, so trace of epsilon prime, we just stick in the trace operator. Now we use the fact that it's invariant to cyclical perturbations. So you put this here, and then we have trace mx epsilon epsilon prime. Okay. Now this expectation we can move inside, and remember we're treating the x's as fixed. So we have expected value of epsilon epsilon prime here. Okay, then and this is sigma squared I under assumption that it's homoscedastic. So we have sigma squared I, so sigma squared is just a number. So then we can pull sigma squared out. We have the trace of mx. Trace of mx is trace of I minus the trace of this, you know, x prime, x inverse x prime. The trace of I, well, this is the identity matrix. So it's the sum of the diagonal elements, and this is an n by n identity matrix. So that equals n. Okay. Now this here, we can apply again the cyclical perturbations argument. So we put this x over here. Then you get trace of I again, because this is going to be I, you know, because these things cancel to form the identity matrix. But in this case, it's a k by k identity matrix, right? This is an n by n identity matrix. This one is k by k. So therefore, the trace of a k by k identity matrix is k. All right? So we get sigma squared n minus k times n minus k. So that tells you that if I divide this original thing by n minus k, the expectation is sigma squared. Okay, so I think it's a really clever little proof. And I guess we did not use that last property from this slide, but this is also true. Okay. All right, so that concludes chapter 7.